Hello, I'm Thomas. I'm a first-year PhD student at IRD and Université Montpellier, and I'm going to present something I did before I started my PhD about mapping informal settlements with a remote sensing foundation model and expert knowledge. So informal settlements are slums, rapidly growing urban areas characterized by unregulated construction, high population density, etc. And according to the United Nations, over 1 billion people worldwide live in informal settlements. We need to map informal settlements to achieve the Sustainable Development Goals, and especially Goal 11, which calls for ensuring access for all to affordable housing and safe housing. But informal settlements are difficult to map with field surveys or socioeconomic data, as by definition they are built outside any legal framework. So geospatial machine learning is a powerful tool to map informal settlements. We can operate under a grid-based paradigm, and that is what we did. We frame informal settlements mapping as a binary classification task. So we define two types of cells, of spatial units. We have informal cells and formal cells, depending on the proportion of the cells that is covered by the informal reference polygon, the ground truss. That is the white shading polygon here. And there is some mixed cells that we don't take into account in our classification problem. And we wondered how to represent these cells in order to classify them. So we can use expert features or deep features. The expert features are rule-based features that we define based on our knowledge of informal settlements and our knowledge of the study area, but they remain simplified to a set of rules that we defined. So they may not capture all the complexity of the data available, all of the available geospatial data. And in contrast, the deep features, there are rich representations learned from global scale satellite imagery. By deep features, I mean features from a model pre-trained on external data like a foundation model. But with these types of models, we are limited to the modalities of pre-training. Most of foundation models are image or image text models. And there are some works about sensor agnostic models. But most of the time, if we need some task-specific data, we can't incorporate it in a model that is already pre-trained. So given the assets and drawbacks of both types of features, we designed a multi-view framework to combine expert and deep features. So first, we extract features from Sentinel-1 and Sentinel-2 images with the remote sensing foundation model. Then we compute other features from the OpenStreetMap Pro network and the Copernicus elevation model. And then we combine all the features in a late fusion approach. So for the deep features, we relied on the Chromar RSFM, that is from December 2023, but that is still well positioned in current benchmarks. And yes, we use the remote sensing foundation models because it's trained large satellite datasets, so it's better than using a task-specific deep learning model. Then we computed 9 expert features. So, for example, from the OpenStreetMap Pro network, we use statistics from the street network because informal settlements tend to be more chaotic than formal ones. From the Copernicus elevation model, For instance, we compute the slope because information settlements often develop on steep terrains. Traditional normalization is more difficult. And we have also two features from Sentinel-2 imagery, but we don't use them in the final framework. We use them only on the single view feature, single view baseline with these expert features. And for instance, we have the entropy because a high entropy is associated with high spectral variability that can be associated with the diversity of the construction materials in information settlements. So all of these features are computed for each cell that we want to classify. Now that we have deep and expert features, we just use one classifier for the expert features, one classifier for the deep features. So in both cases, we obtain a probability for the target class for each cell. And then we compute a mean probability. And we apply simply a threshold on this mean probability to have our final outcome. So very simple, but it allows both classifiers to contribute to the final outcome, and they can still disagree. And it prevents from potential biases from a single view, since the final prediction is dependent on the joint evidence provided by both classifiers. We compared our approach with three baselines. So first, we have a single view baseline for expert features. So we use one classifier with the expert features, one classifier with the deep features. And we have also a straightforward early fusion baseline in which we concatenate deep and expert features in a single feature vector, and then we classify it. We evaluate our approach on Rio de Janeiro, highly challenging testbed for information settlement mapping, because information settlements can share very similar characteristics with formal ones, and then show very diverse characteristics across the city. To assess the generalizability of our approach, we perform the spatial cross-validation across 5 distinct zones. So here is one of a subset of one of the 5 zones. So you can see formal cells in blue, informal cells in orange. And then we perform the multiple runs of spatial cross-validation. So these are results. So first, you can see that expert features outperform deep features. Then we can see that there is no added value of the early fusion baseline. And in the late fusion approach, so our approach, we outperform all the baselines. So there is a complementarity of the feature views, but only in a late fusion approach. This is a quantitative analysis of our results. So it's a visual visualization of confusion matrices elements. So the radius of each disk is proportional to the number of cells in each category. So you can see, so it's only for 2 of the 5 validation zones, but you can see, for example, for zone 1, deep features, we have way more false positives with deep features than with expert features. But on the contrary, we have way more false negative with expert features than with deep features. But in zone 2, on the right, this trend is reversed. So we can see that there is a complementarity of the 2 feature views. So yes, as a conclusion, deep features from a remote sensing foundation model provide rich representation that are generalizable, and expert features can add additional information through task-specific knowledge. But this complementarity is only for the light fusion chains, and future work could explore, could investigate some interpretability mechanisms to better understand the contribution of each features. And we could also work on the integration of urban-specific data like street network data from OpenStreetMap directly into the pre-training of foundation model. And so this topic led to the topic of my PhD that I started at the end of last year. This is about geospatial foundation models for the analysis of urban environments. And for now, I'm focusing on pre-training trade-offs for remote sensing foundation model. So, for example, is it better to, in terms of performance, to pre-train a model on data from all over the world, or to focus on, for example, satellite images only from cities? And then I'm evaluating the models on a little benchmark with urban classification tasks, so local climate zone classification, urban land use land cover, and informal settlement segmentation. Thank you for your attention.
Do we have any question?
The datasets that we use to benchmark, are they public datasets or in-house?
So the first one is a public dataset. It's called LCZ42, S227-42. The last one is we are going to publish it, but it's from public data from Brazil. And in the intermediate one, it's it's from another article, so it's already public, but it's not in a bench.
We have time for one or two more questions.
Yeah. Maybe a slightly controversial question. Why, like I see that the main contributor to the performances in your model is the expert features. So why not try to improve the sources that you put there instead of working on the visual parts, which apparently contributes less to the results?
But I think the expert features are better alone than deep features. But I think here the contribution of both features is quite equivalent.
Okay. And do you plan to work on trying to integrate more external data that could be considered as expert features?
Or just the data without features, like OSM data, OpenStreetMap data?
Yeah, for instance.
Yeah. Yes, but I heard this morning that multimodality for discriminative models is not very good idea. So I will see.
Any other questions? Okay, so that's thank again, Thomas, and good luck with the film.